Hello everyone, and welcome to the 5th webinar in the latest Lab Automation University online series. Once again, I'm Kaylee Thomas, the Events Manager for Lab Manager Magazine, and I will be moderating today's webinar, which will focus on issues in lab automation. Please send us your questions at any point during the webinar, and our speaker will address these during the question and answer session following the presentation. Simply type your query into the question box on the right-hand side of your screen. It is my pleasure to introduce our speaker, Joe Laskowski. Joe is currently the Executive Director of the Institute for Laboratory Automation, a nonprofit organization focused on the development of people and technologies to effectively design and implement laboratory automation and computing systems. Welcome, Joe.
Hi, thank you very much, and welcome to this session where we'll be talking about some key issues in laboratory automation. In the previous sessions, we've been using this elements of laboratory automation chart that we talked about in the first session as kind of a guide. And so far, we've focused on the upper parts of that session. We've looked primarily at management issues, planning, skills. We've talked about policies and practices and management's role in this. And we talked a bit about classes of laboratory automation in the first section. The issues we're going to talk about bring us to the bottom of the chart. We're going to be looking primarily at things revolving around systems integration, the methodologies, the role that standards play in systems and networks. If you go up on Google and you type systems integration into their image search, you wind up with a lot of images like the one shown on the screen. The whole idea when people talk about integration is trying to emphasize the fact that things are working together. And by working together, they get more benefit, more efficiency, better working systems. When integration pops up in systems requirements, we talked about this GALB V last time, it usually shows up in the top part of the diagram under the user requirement specifications. People would talk about having systems and talking about the fact that they want them to work together. They may have 3 or 4 different systems, but from different vendors. But the end result is they want these things to work together cooperatively. And that usually filters down into hardware and software specifications depending upon the kind of systems that you're dealing with. It always winds up involving software, but sometimes hardware if you're dealing with robotic systems. For example, somebody may say that they want an instrument data system to connect to a LIMS or electronic laboratory notebook, or they may want to connect electronic laboratory notebooks to the LIMS systems. The actual communications is a matter of software, but it does involve some hardware components, as we'll see later on. The reasons people deal with integration is looking for a number of benefits. They expect to see a higher level of ease of use with integrated systems. And that's what we're used to when we see integration in document management systems, for example. If you're designing a document and you're working with graphics and it's an integrated system, you decide you want to put a chart in the graphic in the document. You select the place, you pull down chart, design the chart, put it in, and if you want to edit it, you go off and just double click on the chart, make the changes you want to make, close it, and it's in there. You don't have to worry about bouncing around between multiple graphic systems, document management systems, and then creating links to pull things together. That work is done for you. It's also an idea of improving productivity, streamlining the operations. When we work with integrated systems, we expect the number of steps it takes to get a job done to be reduced. It's also a matter of avoiding duplicate data. One of the problems we have in laboratory systems is that because of the way data systems are structured, you wind up with the same data elements repeated in different systems. Particularly, for example, in the example we talked about, where we talked about instrument systems talking to a LIMS, all the data about a sample may wind up being in the instrument system, and parts of it also in the LIMS. So you have a lot of duplication. If you're trying to find information, you wind up having to look in multiple places. You may find part of it in the LIMS system, part of it in the instrument data system, and part of it in the procedure description. The idea is if things are integrated, you should be able to find it in one search, going through one system. There's also an issue of avoiding transcription errors. In many labs that I've visited, you have people printing out information out of an instrument, tearing off a piece of paper, walking over to another terminal, and sitting down and typing the information back in. Every time they do that, every keystroke is an opportunity for an error. So as information is being entered, the person doing it's got to check it. And in systems where it's really critical and they want to be really rigorous about their data handling, they'll have a second person verify it. We'll see some discussions about this when we talk about how this affects medical systems. But the whole idea of integration is that the transfers are electronic, and as a result, transcription errors should not be an issue. There's also a need to improve workflow and the movement of data through lab systems. Regardless of what kind of systems you're dealing with, instrument data systems, ELNs, LINs, take your pick. The idea of integration is to smooth workflow, to make things work easier. And as a result of all these things added up together, we wind up with more cost-effective and efficient laboratory operations. When we look at these ideas of integration, most of our ideas and thoughts focus down here, the lab bench down here where the instrumentation systems are, and on the second level, which is basically the departmental systems, tied together. But when we think about integration, we also have to move beyond the laboratory. Laboratory is now part of the corporate structure where it used to be at one time isolated. Now it's a matter of how we tie these systems with systems that exist in other laboratories and how it can exchange information with process control systems, warehousing and shipping, and then always with IT services. So integration has to be dealt with on a much broader basis involving a larger number of people than it would if we're only concerned with just operations within the laboratory. Our ideas about integrated environments come from experiences that we've had. For example, there are a number of office suites that are available that provide word processing, calendar systems, spreadsheets, presentation management systems, a range of document layout capabilities, email, and other functions. And we all see these things as being integrated environments. And they're available from a number of vendors: Microsoft, Apple, Adobe. OpenOffice provides a very nice one if you want to be in a open source system, and there are other vendors as well. They all have something in common. They were designed to work together. There was an architectural basis built for integration. It wasn't a case where people said we're going to go off and build these applications and then make them work together. The underlying structure to make sure these things work was put in place first, and the applications were built upon that structure. And that's what we need to deal with when we're looking for integration. We've seen examples of integration in other areas in hardware systems. For example, the machines that you're watching this presentation on may have FireWire and probably have USB connections. They provide for easy integration of hardware systems. Before we had these systems, if you want to install a disk drive, you wound up having a technician come in, install a driving card, putting in some cabling, putting the disk drive in place, checking it out, and making sure it worked. Today, you plug it in, you expect it to work, and really surprised if there's a problem. In the telephone diagram on the right, we see actually two different types of approaches to integration. The old-style telephone systems were hardwired and integrated into the telephone network. But the integration was done as a result of hardwiring the phone into the circuits that were buried in walls. If you wanted to move the phone from one place to another, somebody had to come in, disconnect all the wiring, reroute it, reconnect the wiring in order to make it work. At one point, AT&T decided that that was a bad way to work and went off and created two standards that made a big difference and all the difference in how telephone systems worked. One of those standards are modular connectors, little plugs that we have that make things work, make it easy to connect things into telephone wires, connect fax machines together, whatever we have. And the second thing they did was create touch-tone dialing. Those two standards created the telephone industry we have now, allowing things to be connected, moved and reconnected, and still be integrated, and also provide a command structure that allowed things to work. Again, we have the same basic idea. These systems were designed to work together, and they provided an architectural basis for integration. In the telephone systems, it was the modular connections and touch-tone dialing. In USB and FireWire systems, it was the nature of the plugs, how things work together, and the electrical specifications and command structures for how these things work together. In software, it was how applications transmitted data back and forth, as well as the formats of the data files. There are other places where we deal with integration. Household wiring is one. We don't think about that very often as exactly what and how that deals with integration, but there's two different approaches you can take to dealing with it. One of them is to have everything hardwired the way we talked about telephone systems being done. Connecting things together, hardwiring them, that would be integrated, but it would be difficult to work with because if you wanted to move a lamp from one place to another, from one room to another, you'd have to disconnect the wiring and then reconnect it. What we really want in integrated systems is the ability to make changes easily, and that's why we have electrical outlets. But what most people don't think about is that whole wiring scheme all depends on standards. The electrical outlets that we have, and the one shown on the screen, are the result of over 200 standards put in place to make sure that things work. And on the upper right, you can see some examples of why those standards are important, not only for the geometry of the plug, but for example, to make sure that it's okay to plug a 15 amp device into a 20 amp circuit, but you don't want to put a 20 amp device in a 15 amp circuit. So the plugs are designed to make sure that doesn't happen. The same thing holds true with other types of wiring, 220 outlets and so on. The standards are there to make sure that everything works together and also to prevent connections that shouldn't be allowed to make. Again, that architectural basis is designed around connections and protocols for data exchange. When we think about integration, the model we have in our mind is the ability to connect things together the same way we do in our normal lives. Go off to the store and buy something, plug it in, and it works. The problem is that the systems that we deal with in laboratory applications are much more complex than the things that we deal with in our normal office environments. And the problem we have to deal with is that the architectural basis to connect these things together really doesn't exist, at least not for general laboratory applications. And we'll talk about what has to be done to make that happen in a few minutes. We do have some examples where integration is possible and where standards exist to make that happen. We've referenced this item before. It's a microtiter plate used very widely in life science applications. The geometry of the plate, the placement of the cells, the array, the distances, the depths are all standardized. And there are other formats of these cells available, but within each type, everything is standardized. As a result, when an experimenter goes off and buys equipment, he has a choice of different vendors and different models of things, such as plate stackers to move plates around, pipetting stations to add liquids or samples, washing stations to clean things out, different types of readers that can all be mixed and matched and work together to make a functioning system. All because the format of the samples is standardized. We've mentioned clinical chemistry before. Because of contractual limits on charges for testing, the laboratories could not change how much they billed people to get things to work. And as a result, in order to reduce costs and to boost operational efficiency, clinical laboratories went off and built a program called Total Laboratory Automation to make sure that laboratories operated efficiently and reduced cost. Those systems improved communications between hospital information systems in laboratory and also between administrative environments. There were 4 standards that were developed to make this work. The first one is something called HL7. The HL7 name mimics the structure that originally came out for dealing with network standards. when network standards, computer networks first came to being put in place, there were a lot of competing systems from different vendors. And then we had the Open Standards Interconnect standard situation built, and that was built on a 7-layer standard. The whole idea of that 7-layer structure was brought over to hospital systems and provided a basis for communications between administrative systems both in the laboratory and in the hospital. So when the laboratory was developing tests and it had to go off and send information out for billing, there was a standardized means of communication between that laboratory system and the hospital administration system. Within the laboratory, to work with instrumentation, there were originally 3 standards that were put together by the ASTM. The first of those was a data dictionary, a simple document that described what the terminology was that was being used for certain types of testing and test results, what it meant in terms of the structure of those tests. The second was an electrical specification, how signals were going to be transmitted across wires between devices so that communications would take place. Originally these were RS-232 back in the 1980s and now have moved off to more robust standards. The third part of the puzzle was the format of messages that were being sent across the systems. So we had the carrier specification, how signals got transmitted. We had a definition of what the messages look like, and also a definition of what the message formats were and what the contents would be. So those standards gave a very robust way of dealing with data communications. Those standards are no longer part of the ASTM. They've been retired and have been taken over by the Clinical Standards and Laboratory Institute in their standards program and are maintained by them. One of the concerns when this whole standardized structure came out was whether or not the whole industry would go away, whether or not vendors would really participate in the systems because they may not feel they had the ability to make any money. But the people who push the standards believe seriously that all the standardization would improve the marketplace and make it better for vendors as well as the end users. And the quote on the screen is basically an assumption of what their beliefs were. They believed that the total market for automation systems would be greater than it was without them. And that's what happened. The clinical laboratory market has exploded with the ability to create new products. And any marketplace that we can deal with where standardization has been used for integration purposes has exploded, and we'll see another example of that in a little bit. The HL7 format focused primarily on transfers of information between informatics systems, higher level informatics. In our laboratories, we'd be looking at transmission of data between laboratory information management systems and ELNs as an example, or higher level instrument management systems. In the clinical laboratory, it was between laboratory information systems, the equivalent of what we call LIMS, and then the hospital administration systems that were used for billing and accounting. But there are other levels we have to deal with. For example, there's the instrument control and data transfer level that we have to worry about. How do we have things talk to each other that are made by a number of different vendors and have that information be sent and understood? There are 2 ways of doing it. One is to create standards that provide a basis for formal direct communications between these systems. Another is to recognize the fact that differences exist and to provide a mechanism for doing translations. Actually, in clinical environments, both are being used. The second, middleware, is used where systems that simply don't meet the specifications as yet. And what it looks like is something like this. At the top of the system, we have the informatics systems, whether it's a LIMS or an ELN, and then we have a piece of middleware software that acts as a link between instrument systems that have proprietary formats and the standardized format that these systems expect. This system does all the translations in both directions. For example, if you're an experimenter working over here on this system and you wanted to have a balance read with the results being put into a database the system would look like the diagram on the screen. Your command would be sent out. The first thing it would hit is the standardized messaging interface. That would translate the message that you wanted to send over to a instrument-specific instrument-specific command structure that would go to the balance. The balance would respond. The data would move back through the system and into the database. It's a little bit complex, but it works. The same thing holds true when you're working with more complex instrument systems. In this example, a work list, the list of samples that need to be processed, would be generated by the LIMS system. That work list would be sent down through the messaging interface to the messaging structure that reformats the commands into something that the data system would handle, sends those commands to the data system. It does all the sample processing, then has a list of the work list and the finished results that have to be sent back. Those are returned through this interface, reformatted, and then sent back into the LIMS, and it works. Those systems are routinely used in clinical environments, and there are some vendors that deal with them in industrial environments. The third area we need to look at are standards for instruments. And this is an area that's had a very checkered past. In the 1990s, the Analytical Instrument Association, which has since changed its name, created a project that started in 1992 to develop something called the ANDI standards, Analytical Data Interchange Standards. Relatively little input from the user community. And the idea was to create data format specifications for a variety of instrumentation. The first one they hit was chromatography. The project was begun with a lot of fanfare and a lot of attention in 1992 when a gentleman by the name of Dave Nelson proposed the project at Pittsburgh conference. A lot of activity, the room was packed, and there was a lot of interest. The project terminated around 1998. And part of the problem was simply getting people to work on it. There wasn't that much attention being paid to it. The results were a specification that came out for ASTM for chromatography, which was updated in 2009, and is still being used in some applications, but not very widely. What this tried to do was go off and take all the information about a chromatographic process, about the data from that process, and incorporate it in a file format with standardized structures and numbers, numerical formats, so that any system could pick it up and work with it. The same thing was done for mass spec, although that never was ever formalized into an ASTM standard. In addition, work was done funded by the U.S. Army Corps of Engineers for ICP processing, for metals analysis. Now, while the primary ANDI standard was looking at simply encapsulating information about a standard, when we did the work for the ICP, we recognized a problem. That is that the sample data by itself is meaningless. It needs a context. It needs to be associated with standards. And that was one of the failures of the ANDI program. If you think about how instrumentation works, samples by themselves are useless. They need reference standards to understand both qualitative and quantitative analysis. So you need information about standards to go off and create a calibration curve, and then you apply the calibration curve to the samples. And all that stuff has to be kept together. Otherwise, you start losing the context of the data. And if you start losing that, then you no longer have really a good, solid, regulated environment. So what we need to do is understand the structure of a sample tray. We need to know which elements are standards, which ones are samples, what the ID of the samples are, and when it comes to the standards, what their value is. And all that information has to be kept together with the sample data in order to make use of it. What we really need is a structure that looks like this. We need an experimental description that, when it's used, creates a run of samples that may have one or more trays, depending upon how many samples are in the run. For each tray, there's a separate description that says the first vial is a standard, the second vial is a sample, and so on through the entire system. It says which ones are duplicates, and so on. And then for each vial, you have the ID for that vial, all the metadata that goes along with it, and the text measurements. This kind of structure is being built in a standard that's currently in process, and if you look up the URL, you can find out more about it. It's called the Analytical Markup Language. It was originally driven by NIST, but is now being funded by a number of people, and this work is still underway. And I'm not quite sure where they are in the process of actually having that resolved as a full ASTM standard. But this is the kind of thing we need to think about. We had to move away from the experiences we had with other standards, where they were simply encapsulations of one sample's data, to looking at the full context of how the samples were being run. What people really want are systems that work so that people can work better. They also want the ability to integrate systems of their choice. They want to pick the products that are tied together and not have vendors choose them for them. They want it to be done easily, and they want it to be supportable. Unfortunately, and that integration, as we mentioned before, needs to occur not just in the laboratories, but in the people working between the laboratories in multiple labs and different departments, being able to exchange information. The reality of today's systems, though, isn't quite there. What are your options for getting done, because the standards really aren't in place to make things work? Vendors are talking about integration within their product suites. They are providing collections of products that they develop, or they work in partnerships to put together a collection of materials and collection of programs that work together. They provide the communications capability. One of the problems that you have with this is that you're basically, when you talk about an integrated environment, you're not talking about what you want to plug in. You're talking about what they offer. So the question is whether or not what they offer is enough to work with for you. Is it going to really solve your problems? And what happens when you have things that you want to integrate that aren't part of that product set? Another thing that has occurred frequently are vendor partnerships talking about integration. 2 vendors or 3 vendors come together and said, we're integrating our products to make it easier for you to work with. This works out best, or most frequently, when you have people who don't have competing products within their product set, but recognize that there's a need to meet the user's requirements. The common one is chromatographic data systems and LIMS products. But there are 2 ways these partnerships can go. They can be marketing partnerships, or they can be really robust technical partnerships. Marketing partnerships are usually a demonstration of how things work. 2 systems actually do work together, communicating. The problem is for how long. We talked last time about product life cycles and what impact they have and what you have to deal with upgrades and what happens when products are retired. You've got to deal with the same issue here. If it's a marketing partnership, the odds are that when upgrades occur, they aren't going to reinvest the engineering resources to make sure that these things work. If it's a really solid, technically based partnership, one where they've sat down and worked out an integration mechanism that will survive upgrades and they're willing to support it across upgrades, you have a different story. You have a story that you can actually live with. You may be able to extend the integration set, that is the suite of products that are there, but you're going to have to support it, including across upgrades. And upgrades are really the serious test of how well the integration was done. This is far from the ideal case, but it may be your best bet. And one of the things you've got to look at when you look at these suites is evaluate the type of products that you're dealing with and decide if you're going to integrate something, whether or not it's simply better to go off and scrap what you have and buy a new piece of hardware or software that is already integrated for you, or deal with the cost of doing the integration. and support. Some vendors have taken a very interesting approach. There are lab execution systems available in the marketplace, systems that guide you through the course of executing an experiment. They're good ones that have taken a completely different approach to integration that works. What they'll do is replace the print command in the computer system that's generating the instrument data with, instead of being printed to a printer, they print to a PDF file. That PDF file is sent off to the lab execution system where it's parsed, it's analyzed to extract the information out of the system. This works. The first thing you do is a test case that generates the PDF file, and then you work with the system to make sure it understands what the data is that you're working with and what information you need to deal with. The PDF provides device and vendor independent format to work with. So that's reasonably good. The place you get into a problem is when you have to work backwards. If you have to look at some of the information that's in the execution system and trace it back to the original instrumentation information, there is no clean path going back. You've got to go back and actually do the trace back manually. The other problem you run into is that when you look at a graphic that's part of that PDF, it may be a chart, it may be a chromatogram, an infrared spectra, thermal analysis, what have you. You look at it and said, okay, I want to look at that graphic in more detail. You can't. The information that's provided as part of the PDF is the limit of the information that's available to you. If you want more detail, you have to go back to the original system and make sure it works and get the information there. If systems are being upgraded and changed and retired and data is being archived, you've got to go back through those archives to go off and find it. And that's another example why, when we talked about virtualization in the last sessions, why that becomes important. There are vendors in industrial laboratory environments that are providing middleware systems to make that transition easier. They're providing the middleware so that you can go off and write your integration protocols against the middleware, and then they'll take care of the translation all the way through. The problem you get into is that you're basically locking your laboratory into that vendor's product set. So you need to go off and evaluate that vendor very carefully and make sure that they've got a solid reputation and they're going to be around for a while, and that those products are going to be around for a while because your whole lab is going to be dependent upon them. And if you're going to do customization, the question is, are they going to do it for you, or are you going to do it, and at what cost? You've got to decide whether or not it's really worth it and who's going to provide support for future versions. There are also vendors who are all talking about bypassing standard laboratory systems to go directly into corporate management systems. For example, some people who are providing laboratory execution systems are talking about skipping the LIMS system and doing the integration directly with enterprise resource planning systems. This is a somewhat dangerous environment to deal with because the systems that you're dealing with in the laboratory are difficult enough to manage. How are you going to deal with integration when you're managing a corporate system that may be upgraded without any concern for what's going on in the laboratory, or changed or modified, and those changes and modifications affect the way your laboratory works? These things are being proposed seriously by ERP vendors, and there's something that you can consider, but you need to be careful about, because the level of integration they're providing may lock you into those systems and also may be volatile as you deal with upgrades and product changes on both sides of the integration. Another approach is to manage the integration process yourself. Decide that, okay, it's important enough to work with the products you have, and then make those connections on your own. This can be a very significant development effort. It's going to be expensive. It'll give you what you want. You're in control, but it's going to cost you to make that happen. The results are going to be subject to risk if anything changes. Again, it's the product upgrade issue. We have multiple layers of products, operating systems, database systems, end-user application systems, all of which will change asynchronously, and you've got to be careful to make sure that the way systems are being designed, that they can survive those changes. You also may find yourself, if you're not careful, about locking yourself into a product version for any of the integrated elements, because changing the product version may cause you considerable development effort. If you do want to use this approach, one of the things you want to make sure that you deal with is something called device-independent programming methods. I'm going to show you an example of that, what that really means. And we don't want you to become programmers, but we want you to understand what the concepts are, because if you're coming out with project requirements that require this kind of integration, you at least know what to tell the people who are doing the contracting work, how they should go about getting some of that work done. And the example we're going to use is computer graphics. Computer graphics today is a very large industry. You can buy systems, you can buy software, you can buy hardware, you plug it together and you expect it to work. And you'd be really surprised if it didn't. Applications is if you're a really serious gamer, or if you're doing graphics development, video systems development, animation development, where hardware requirements become important. But for most applications, hardware doesn't matter that much. You don't even think about it. But the hardware and software systems can get fairly complex. The software you work with is governed by pieces of software. In order to generate graphics output, that software generates commands that go to a graphics card, and a wide variety of them available. Those graphics cards are what generate the actual image you see on the screens. In the 1970s and 1980s, life wasn't graphics industry. It wasn't very happy. Every vendor had their own graphics library. Every vendor had their own graphics hardware. And you couldn't mix and match hardware and libraries. If you liked a particular vendor's hardware, you dealt with their software. If you really liked their software, you limited your hardware capabilities to what they had available to you. Even on things such as PCs, we had a wide variety of graphics hardware, then different software packages played with in different ways. The ones on the screen are just some of the examples of various types of standards that existed for graphics hardware. EGA, VGA, CGA, Hercules. Combo cards were an interesting addition. You put the card in place, you ran a little program and it said, the next time you're initialized, you're going to look like a VGA card. You do what you have to. You're going to work with a different program. You rerun the program, that first piece of software, and tell it now you're going to look like an EGA card because it's working with different pieces of software. And then you have to make sure that the hardware, the display hardware, supported it all. So things were really a mess. What happened was that the user community came together and said, we're not dealing with this anymore. We want standards in place to make sure things work together. We want any software we have to work with any hardware and work with display monitors. What happened was that a standard was proposed out of Germany, and it was signed off by ANSI, and it became the standard for graphics for doing software development. But what they did was they separated the software from the hardware and the command structures so that any type of software could talk to any type of hardware and output the results to any type of display, basically creating the systems we have today. That's what device-independent programming is all about. When you installed a new piece of hardware, you installed the driver for it, and you didn't have to worry about changing these applications because they were outputting commands in a standardized structure that these device drivers were expecting you could deal with. So you didn't have to go off and recompile, reinstall your software simply because you changed the hardware. Things simply worked. And that's what we mean by device-independent programming methods. You keep all the logic about the stuff that's going on in your instrumentation, about your systems, separate from the actual commands that go out to the instrumentation. Confine those to one part of the system. So if you have to make a change, the change is made in one place and not scattered throughout your code. This kind of standardization, this kind of structure, has created the graphics industry we have today. The graphics industry we had in the 1980s was really fragmented and difficult to deal with. Today, it's a piece of cake. We want the same kind of thing going on in instrument systems. So we've talked about vendor partnerships and doing it yourself. If you're going to go off and do it yourself, whether you're going to do it yourself or not, one of the things you need to do is make sure you build a lab automation plan that's really flexible, that's really thought through. What you want to do is put the entire structure on paper so you know how you want things to work. And then as you buy systems, you buy them not just for their own capabilities, but for their ability to work according to the structure that you put in place. You want things to be fairly flexible because the systems are going to change and you never know what new products are going to come up. And when you do it, you need to evaluate vendors and inter-vendor partnerships to make sure that they're stable and you know where they're going. Where are you in the product life cycle? We talked about product life cycles before, and you don't want to worry about getting a product in this area that's going into retirement. You don't want to worry about a product that's currently going off and being modified by new generation. It becomes part of your vendor qualification and part of your evaluation of what you're building. You really have to plan systems ahead to make sure they work. How does this affect your product requirements? You really need to be realistic and really evaluate risk when you're talking about integration. You want stability, you want the ability to make things work together, and you've got to look realistically at just how well that's going to happen and how realistic that requirement is. If you want to keep up on what's going on in integration, one place you can look is a website that's on the screen, the Integrated Lab. It's managed by a gentleman by the name of John Trigg, and he keeps following the whole area of standards and integration, posting information about what's going on in the field. Unfortunately, what's going on in the field isn't really good. In Milan, in September of this year, there was a meeting held as part of a larger conference, and the bottom line was users are frustrated. They're frustrated by vendors that are taking their individual approaches, not working together, and not meeting users' needs, that the efforts are currently disorganized. Basically, we're in the same position the computer graphics industry was 30 years ago. Since then, that industry has benefited from users and vendors according to standards. But what really needs to happen is that the user community, not the vendor community, but the user community, really has to come together and say, this is the way we want things to work. It did work in the clinical chemistry environment, and it can work elsewhere. One thing that happens that's going on now is you're seeing a lot of marketing hype about the idea of paperless environments. Sounds like a nice idea. What does that really mean to you? Does it mean more efficient laboratory operations? Does it mean going green by reducing the amount of paper and ink that you're working with? Does it avoid duplication of records, not losing information, not losing data and reports, having everything organized? Is the paperless environment really a goal, or is it a result of using technology better and really an end result of making sure that integration occurs so that we don't need paper systems all over the place? Right now, we're seeing paperless environments being pushed in medical records, being mandated in part by the government. And as medical offices go through this, you're seeing a lot of turmoil. If you're looking for data in a doctor's office, you may find out that statement on the screen, which I've actually heard, is we're going paperless, we can't find things. There is the stuff before they went paperless, there's the stuff they went after paperless, and they're not sure where things are. They have to make sure they manage the transition between one environment and the other. The same thing is being seen in electronic data capture in clinical trials. Originally, when you did a clinical trial, you interviewed a patient, all the information was written down on paper. The next step was telephone interviews, where all the information was recorded and then transcribed. Web systems are currently being used, so a patient can log into a web system and describe what the results are for whatever medication that they're on. But you have to be really careful about how we manage the transitions. There's a lot of transcription there. What's happening too in some areas is the transition going from paper to paperless is a result of people typing the information in from paper into computer systems. And that requires a lot of redundancy. In some cases, it's two people typing the same information again in and having the systems compare them and make sure that they agree. It's really a bit of a problem, and you've got to worry about what happens to the paper information once you're finished with it, because that really was the original primary record. So if you're going paperless, you've got to worry about how that whole transition takes place. The real question you need to ask and you want to address is, what problem is it you're trying to solve? By going to a paperless laboratory, is it really an arbitrary or unrealistic goal? If you really got to leave yourself some slack and make sure that you're not painting yourself in the corner, because some of the systems you're working with may not work in a paperless environment. Some systems are geared toward generating paper, and you may have to replace those systems to literally avoid the paper issue. Informatics and lab automation is really undergoing a transition, and it needs to be driven by the user community. The lab is no longer being viewed as an isolated environment. Lab automation technologies, the kind of things we've been talking about, are really the way the work gets done. The whole nature of the work is changing. And we have to start looking at strategic planning as a replacement for stepwise and incremental changes in the way labs work. It's not simply a matter of, we used to do it this way, now we're going to buy something to help us and do a little bit better. A plan has to be put in place, and whatever you buy has to meet the plan. We really need to start telling the vendors what kind of products we need and what those kind of capabilities those products should have. Vendors, in some cases, are working blind. They're building products that they think you need, but they really want your input to make sure they're building the right products with the right capabilities. You need to take advantage of that and really push on the vendors to get the kind of products you want. We need to make sure we drive towards technologies that will help us realize integration and reduce paper goals. Again, it's completely user-driven operations. And lab management really has to be active in project and technology planning. It's part of the change that's going on in laboratory operations. It's not just people management, it's technology management. In the next section, we're going to start bringing some of this stuff to a head when we start looking at products and technology, looking at informatics, trying to decide what products are really appropriate for your lab, or helping you decide what products are appropriate for a lab, and how they should work. We're also going to look at something which has risen in the past, been put to bed, and come back to life, and that's the whole build or buy decision. When laboratory information management systems first came out, there was a question of whether or not you should build them or buy them, and everything went towards the buy routine. But now that we're dealing with electronic laboratory notebooks, that's come up. We'll take a look at that issue and what the complexities are. We also have to take a look at how regulatory requirements are there, making sure we know what we're doing when qualifying candidates, and really what the trade-offs are. Any questions?
Hi, Joe. Thanks. Yeah, we have a couple that have come in. The first one is, what is it really going to take to make integration possible?
All right. Well, as we've probably gathered, standards are the key thing for integration. You can't have integration without standards. It's just not going to work. And what's going to have to happen is that the user community, it's you guys listening to this presentation, are really going to have to start demanding that this stuff gets done. Otherwise it won't. There are too many conferences where people have talked about standards, and one of the things you hear about is, well, we ask the vendors for standards and they don't do them, or they push back and they really don't hear us. The vendors make their livelihoods by selling products to you. If you don't buy them, they go out of business. If you demand those standards, the implementation of those standards, it'll work. But it's not the vendor's responsibility to make those standards happen. It's yours. They'll respond by incorporating standards if they know that there are standards in place that everybody is willing to support. And that's part of the problem. We're dealing with a very fragmented market. And you've got to make sure that the standards are really widely applicable. The vendor doesn't want to go off and invest engineering resources in developing something that's only going to deal with 10% of the market. If you can guarantee them that you're going to deal with 80% of the market, they'll pay attention.
Okay, and the next question, which is our final question, is why has the standards issue not been resolved after decades of talk?
The biggest problem is market fragmentation. The way people deal with the science market is they deal with it from the standpoint of industries, pharmaceutical versus petrochemical versus environmental versus something else. And within those industries, you have people dealing with things on the basis of technique. We're mass spectroscopists, we're infrared spectroscopists, we're chromatographers, we're rheologists, we do physical properties management, physical properties determinations. And everybody looks at it as, well, we need a standard for our stuff. And it's going to be different than the standards somebody else wants for their stuff. The standards that might be used for mass spec in environmental work might be different than the standards somebody wants for mass spec work in pharmaceutical applications. As long as we have that fragmentation, this market is going to come together to make things happen. What we really need to do is get past the silos that we're working in, get past the fact that this idea that everybody's needs are different, and realize when it comes to data interchange, everybody's needs are really the same. The differences are in how you use the equipment, not what the equipment does. And once we start realizing it and said, all right, everybody who's working in mass spec wants to deal with a specific standard, and the differences really aren't in the data formats, it's how you use them. So you come up with a standard for the data format, and the same thing holds true for other instrumental techniques. Then it'll work. But as long as we deal with it on a fragmented basis, society by society and industry by industry, it's not going to happen. You got to come together and work together to make sure that this thing occurs.
All right, well, thank you, Joe. This brings us to the end of today's webinar. If you have any further questions, please reach out to Joe directly. As we know, he is the true expert in this field. Once again, I would like to thank you all for taking time out of your busy schedules to join us today. We look forward to seeing you back here again on December 18th. Thank you and goodbye.